Hello everyone and welcome to tutorials on code-aster and Salome-Meca. And in today's tutorial we are going to see the response of MDOF system subjected to base excitation, which is also called as support excitation or seismic excitation. For this particular tutorial we are going to consider an 8 degree of freedom system model, and the model is as explained over here, as drawn over here, and the parameters are explained over here. The difference being, here we have, as compared to earlier cases, here we have more masses, that is instead of 3 masses we have taken 8 masses, and similarly 8 springs. And earlier we had force which is acting at one of the masses. Now instead of that we are subjecting this system to a base excitation which is xg double dot, as mentioned over here. This is acceleration, and the acceleration is given by sine 2 pi ft, where this f is equal to 2 hertz. This is very similar to what we had seen in the forced excitation part, which we applied a force at one of the nodes. That was, I think, the force was 1000 sine of 2 pi ft. Now instead of that, the acceleration is simply sine of 2 pi ft. If you write the governing differential equation and express it in a matrix form, it will be mx double dot plus kx is equal to minus m1 xg double dot, where this 1 is the vector of ones, vector of only one values. Okay, and as I mentioned, this xg double dot, modeling of this xg double dot in the code-aster is same as f of t, that is you can give input of xg double dot as f of t. However, when we apply it on the structure, there is slight difference, and that I will explain when I actually go for the modeling part. One more thing that I am going to do here, that is in the difference in the modeling aspect, and that is, if you remember, we had a segment like this, and I used to create nodes on it and then join them. So instead of doing it that way, what I am going to do is I will create this first element itself first, and then I will use multi-translation in the Salome interface and use that multi-translation to create all the remaining elements. So as a result, what will happen is I will have this element, and then that will be copied over 8 times or 7 times, so total it will be 8 elements. But when I discretize it, actually when I use, because of this multi-translation, each element is now separate. Each element is separate, and as a result, when I discretize it, the discretization is going to be like this. This is first element, then second element will have this kind of discretization, then third element will be like this, fourth element will be like this, and so on. What I mean here, actually this is not like there is gap, vertical gap in between them. What I want to specify is that there will be 2 nodes at the same point, because each element is now separate. So once I do this meshing part, I need to make sure that I join these 2 nodes together, or I merge these 2 nodes together. So that I can do in Salome interface. That I will explain when we start modeling part. So other than this, there is not much difference, and most of the things will be repeating the same thing that we have done in earlier 3 degree of freedom system model part. And one more thing you should remember is that this excitation, external excitation, is xg double dot, and that has to be multiplied by matrix m. This one will be taken care of by the software, but this has to be multiplied by matrix m. So that I will explain again once we start the modeling part actually. So only difference that you are going to see in this whole part is this, how I am going to draw the geometry and then adjust the mesh accordingly, and then how I am going to apply this base excitation. Remaining everything is almost the same. So let's start with the actual modeling part and the actual solution in code-aster. as I mentioned, the number of nodes you can see here are 16, which is not appropriate since we have only 8 masses and one fixed node. So total number of nodes should be 9, whereas there are 16 because of the multiple nodes at same point. So now I need to merge the nodes. Here the tolerance is 1 into 10 to the power minus 5, which indicates that if two nodes are having distance less than this tolerance, then those two nodes will be merged. And it says that 7 groups of nodes successfully merged, which is as expected. Okay, so now if you see the mesh information, you can see the nodes, number of nodes 9 as expected. So now the mesh is as I wanted. Now let's move ahead and create the groups. Here, apart from these two commands, I am also providing few more commands, which is interpolation, right extension and left extension. The meaning here is, if suppose value in between the values that are specified using this list are required, then I'm telling it that that value should be obtained by linear interpolation. Then right extension, that is, right now the value is from 0 to 10 pi. If suppose the code needs to have a value more than 10 pi, then it is called as right extension, and that right extension should be either constant, excluded, or linear. I am specifying it as linear. And left extension I am excluding because it is a function of t, and before time t equal to 0 it doesn't make any sense to give any value, so that should be excluded. As usual, I need to specify two boundary conditions. First one is specifying all nodes to have zero displacement in y and z direction, and then specifying the fixity on the left node. Other than this, there is no load, only the fixity, and then all nodes are constrained in y and z direction. And see here, I am going to fix the left node. Although this fixed node will be provided or excited with acceleration, even then I have to specify it as a fixed node, because that is the fixity is the condition at the left end. Now I have completed boundary condition and load, yet I have not specified the actual load, that is the acceleration, so that is to be supplied at the left end, and that can be supplied by a command called calc-char seismic, which means calculate charge, that is load, seismic, so calculate seismic load. However, I cannot use this command right now, and the reason being, it will ask me for mass matrix. Actually, what this calculates is, if you remember the equation that I had written on this slide, that is mx double dot plus kx is equal to minus m1 xg double dot. So the right hand side, m1 xg double dot, that is calculated by this one, and it is obvious that it needs mass matrix before I can use this command. So therefore, to get the mass matrix, I have to first go one step ahead and calculate this mass matrix. I have calculated both mass and stiffness matrix. I am not going to provide vect assay as I provided last time, because this is used for loading and not the supplied base excitation. Now once this is done, again now I have mass and stiffness matrix, and using mass matrix I can apply this boundary condition or this supplied excitation using calc-char seismic. Now there is a problem with this, and that is maybe because of the aster steady module itself, which I think will be corrected in later versions. But now what happens is, if suppose I click on this calc-char seismic, then the command being grouped in BC and load, even though I am applying it after pre-analysis, it will be clubbed over here in BC and load, and as a result when it writes command file, these two commands will be together, the boundary condition and then this calc char sesame will be together, and then calculation of mass matrix command will be later after that. So effectively what happens is, this command here over calc char sesame, which is over here, it will ask for mass matrix which is not calculated because it is calculated in this step, so it is obviously going to give error. So to avoid that, what I need to do is, I need to make sure that the command calc char sesame comes after this, and there right now I see only one way of doing that, and that is creating a new stage after this. If I do this, then all the commands will be now placed in this stage and the sequence will be preserved. If I don't do this, then the command will go in the boundary condition and load, and as expected there will be some issues. So I don't want that to happen. So now let me do this in stage 2, and in boundary condition and load I can supply the calc char sesame, and since it is acceleration, I am mentioning it as name as a char mono appui, which means this is used for the cases where you have only one acceleration provided at all the supports. Now we have only one support here, so it is by default going to be this itself, but you can also have multi-support excitations in code-aster, and that we will see sometime later. Now we have only single support, and all the support are going to be excited with the same frequency, hence all the supports are to be excited with the same acceleration, and hence I am using this yes. Then supply this mass matrix, and then direction, it is in x direction, so 1 0 0. Okay, and now once I have this, all the boundary conditions and loads are applied, actually specified but not yet applied. Now I can perform the analysis, and there I can apply it. This is not harmonic analysis, this is transient analysis. Calculate in physical basis, and type of calculation is transient. Calculation should be based on Newmark's method. Here I will provide vect assay, and multiplier function will be sine vals. So what I am doing here, I am not providing load, that boundary condition here. Instead of that, I am providing this acceleration calc char sesame. This is like calculation of seismic load, as I mentioned earlier, and that has to be multiplied. That is, this is minus m. That has to be multiplied by xg double dot, which is sine values function. So I hope this is clear now. And one more thing I want to specify here is that while testing this before recording, what I found out is that by mistake I had not clicked this model, and as a result, when I tried to do the next step, that is output, it didn't show me the result part, this part, response transient, this part. And so I went back and corrected this, and I ticked this model part and again tried to see the output, but again, because once it was not showing, afterwards it never showed me no matter what I did. So the only thing that I had to do in such cases was I saved this entire aster study, that is just using this save, and I reopened the same file and then tried it, and it worked without any changes. So this may happen in this particular case, and it's obvious because aster study is still work in heavy development, so such things will be there. So try to follow the steps as I have mentioned, and don't miss anything in the middle. If you miss it, not a big deal, just try to correct it. If it is not working, if it is not working as expected, then just save the study wherever you are, then reopen it, and it is likely that it will work. It is most likely that it will work. Okay, so now let's move ahead. And then output. I'm going to take output as full GUI output, all steps I want. Okay, it happened again. I think it happened. It's a good thing that it happened, because now I'll be able to show what happens. Anyway, so I'll say okay. I will just delete this part. Okay, and I'll save this. Then so now for output, let me create another stage itself. See, now it showed. So earlier it was not showing, now it is showing. So this happens sometime. So if you are confident that you have whatever was there was actually perfect, whatever you have done is correct, then just save it and reopen it, and it will work. So this will generate the output in which can be processed by ParaView. And apart from this, I also want to have graphical output, graph for the, let us say, node 1, n1. So to do that, I will go here and reco function result. For n1 I am calculating, so n1, and then I want displacement to be plotted for n1. Component dx. Parameter should be time. So I'm trying to plot or get the function which is function of t, and the displacement as a function of t. Okay, this is enough. And then I will output that in impr function using xmgrace. So it's done. Let's save this and let us execute it. Now this third stage will take a lot of time, significant time. The reason being, it has to save all the time steps, and the output file is also going to be bigger than what we had seen earlier. So that's why in dynamic analysis, actually getting the whole output is not recommended, especially when we will go for nonlinear analysis. That's really not a good thing to do. Extract the part only which you require, that is only if suppose you need only displacements, then only extract that part, don't extract the whole model. Okay, so execution is successful, and now we will see the output what we have obtained. This one n1.eps, and this is the response. Now to ensure that whatever response we have obtained is right or not, I have written one script in Python using Jupyter and NumPy, of course, NumPy and SciPy. So I will now try to execute that script and see what response we get at the node 1, so that we will just verify the answer. So this is the Jupyter notebook which is written for solution of MDOF system. Let me run one by one each cell. Here the definition of ODE, and you can see here this is K matrix 8 by 8. Similarly, M matrix is defined here, and then solution for this minus m1 and xg double dot is sin n by 2t. So let me execute it. So this indicates that it is running, so let me wait. Done with the execution, since I got the number over here. Now let me plot it. This is it. So if you can see, this plot looks similar to what I have obtained over here. that's it for today's tutorial, and let's hope to meet once again with another tutorial. For the record, let me mention that I think this is going to be the last tutorial on discrete dynamics part, and I may consider taking the continuous dynamic part from the next tutorials, and then some modeling aspects, and after that we will move to nonlinear part. So thank you very much.